Hi, and welcome to our presentation on the Autonomous Pool Cleaning and Safety System presented by Yichu Chen, Joe Davault, Slater Heil, Parker Meinecke, and Andrew Whigham. So a brief overview of our presentation. First, we're going to go over the key problems that we're trying to solve. Next, we're going to go over some of the background data and research that is applicable to those key problems. Then we're going to give a brief overview of the key pieces and AI component types that contributed to our solution. And then we're going to finally go through the design challenges and AI complexities. A few of the key problems that we intended to solve with the implementation of our system are pool water quality, swimmer safety, environmental factors, smarter pool care, and less effort for pool maintenance. Next. So some of the background data associated with these key problems is that on average, there are 372,000 drowning deaths annually, and of those deaths include 700 children in the United States alone. And the implementation of our system would hopefully, with its security feature, be able to reduce the total number of deaths. Another of our key areas of focus is trying to keep the pool clean, and by that, we're going to try to minimize the presence of harmful bacteria. On average, there are about 3 common types of germs that exist in pool system, ranging from E. coli to Giardia. And by simply maintaining the chlorine level at an acceptable level, these can be mitigated in less than an hour. Next, we are striving to reduce the effects of water evaporation and the effects on the environment. On average, around 25 to 50,000 gallons of pool water evaporate from a standard swimming pool each year. And so by monitoring and mitigating factors that contribute to evaporation, we are hoping to better the environment. Also, on average, the cost for pool maintenance and care ranges around $2,400 a month for an individual pool owner and can be even more than that. And by developing a system, we hope to reduce the costs associated with general pool maintenance. As part of our background research, we found that various components exist to solve each of these individual needs, but there's a lack of a solution that is all-encompassing and can solve all of these problems. Some of the examples include a simple chlorinator that floats in a pool, and those cost around $8, to complex modules that can be modified to existing pool hardware that dispense chemicals but do so in a very inaccurate way. And with through the use of our system, we're hoping that we will be able to not only develop a system that can address all of these needs, but one that can also do it in an intelligent manner and can actually predict and solve any issues that may arise for any size pool.
Okay, Slater, thank you. I'll take it. So this is our key pieces, and this slide, what we're going to do is cover the architecture that was used from left to right. I'll be covering it. This is a distributed architecture with part of the system running at the remote site. So wherever the pool is located, part of the system will be running there. The remote part of the system includes the sensors that run on site, and they produce what's called a sensor array. And the ETL portion of the solution also runs. We have a number of functions that can be run locally, like sending out basic status, refilling of the pool. The things that were a round trip to the back end was not deemed necessary, though we have enough functionality running at the remote part of the solution that can carry out those operations. For things that include the AI portion of the solution, there is a RESTful call that gets sent from the client out on the remote side that goes, and they talk to a set of ingesters or nodes that are just on the inside of the solution, or the inside the system we have that's in the cloud. And there are a number of ingesters will read the information from the field, and and it'll post those out to a set of topics that can be read. So these topics are regularly polled and read by our classifiers. And these classifiers are where our AI is running. So for example, for the sanitizer and pH part of the solution, we have a number of classifiers that have been trained and are able to help us classify the nature of the pool, the level of pH, the level of sanitation based on the incoming vectors. The same thing with the water management system. We have an activity processing model that's been trained up, and as the data comes in and is processed, they're able to talk by posting their topics, and those topics are read by the action controller. So in the action controller, we actually have the ability to talk to our procedural learning and our declarative learning, and also our weighted algorithms. And by using those from previous events, what we call post-event data, we can actually use a weighted algorithm to help our classification. So in the case of image recognition, we can go back and look at the historical background information and compare it to make better classifications. So data is, and we also need to, if you see at the top, there's an account management system, which is part of the back office. In most cases, there is static data, like the pool size or the type of level of service, things that we need from the account management service. So the classifiers also have the ability to reach and get that information from the account management system. So once the classification is made and whether some action is taken, that's either to notify the customer or to dispense chemicals or replace the water. All right, next slide. Okay, some of the design challenges we faced. So the system was broken up into three areas: a cleaning system, a water management system, and a security element or security part of the system. So one of the challenges we ran into right away was the fact that the nature of our data. We have fairly structured data. We don't have large data sets, and so trying to fit our data models onto say convolutional or recurrent, particularly for the pool cleaning, was not fitting the way. And so we looked at other models, and we ended up finding models that were easier to use, easier to train. And so in the case of the cleaning, we ended up using logistic regression models, and we felt that we could get the same results with those. In the future, once we have collected more data dealing with pools, we think that then we'd be a better candidate for some of these more robust models, like a long short-term memory model, where we could do more predictions. So in terms of the image and security portion, one of the challenges we faced was in trying to identify if someone was under distress. Given more time or a better understanding of the problem, or better technology, or more funding, perhaps we could have done something differently. But for this solution, or for this project, what we thought made sense was just to simplify the model so that we could just identify whether something actually was or was not in the pool. And we do that by not just looking at the camera image, but also validating that against the movement of the pool. So if there's motion and there's movement, then we put those together in sort of a weighted relationship, and that's how we classify that. Similar problem that was related to that was also trying to quickly identify if something was in the pool or not.
And that's something I can speak to in the next slides.
Okay. So, and just finishing up, the final one was in our the water movement. One of the challenges we faced was that we had a sensor in the water that would check movement, and the problem with that was that the waves would form and we'd get false positives. So we added a wind sensor to help us with additional data, and in the end we felt we could get suitable results from that. So I'm good. Next slide.
So our AI solution, as Joe had mentioned earlier, the way our data is structured, it ends up being fairly limited to our pool intruder or pool inhabitant monitoring system. And so this system works by using 3 sensors: a passive infrared motion sensor, a video or color image data camera, and a E-tape strip sensor that's on the edge of the pool that will measure the water level as it fluctuates. Now, all of these sensors provide, of course, raw data to the system. The motion sensor provides something that is essentially just a 1 or 0. And so the goal of this AI solution was to make each input basically a 1 or a 0 so that it can be properly weighted and ranged and correlated when making that final decision. So the camera data provides JPEG. It's converted into a bitmap, and that's where our AI solution, the convolutional neural network, takes that bit, it's a 256 by 256 by 3 image, 3-dimensional matrix that the CNN, which is a trained model, it's trained with the scene of the user's pool background. The model itself provides a background subtracted image, and that background subtracted image on its own doesn't provide us with any information. So it has to be processed with fully connected layers, and that kind of fully connected layer is able to provide us with a digital 1 or 0 saying there is either an object in the pool or there is not an object in the pool. And the strip sensor provides a resistive output, which using a simple voltage divider circuit, a 10-bit ADC, and mapping that to a 10-bit range, that can be essentially taken into a simple algorithm node in our ROS system. It averages it and can basically give us the same thing, a digital 1 or 0 saying there's a limited amount of activity or there is high activity in the pool. Part of our AI solution includes using memories, and this memory system works by both storing the data that we're receiving when there is an event such as a distress swimmer, and using that same memory store to basically say, oh, there have been similar conditions that led to an event prior to this. When those similar conditions occur, the memories can say, it will provide a digital 1 to say this has happened before. And so these all weight together, these 4 things weight together here with a simple algorithm that uses weights that change over time depending on essentially what kind of data comes through. So we have a data iteration graph in our paper that can be viewed to see how these weights will change over time. Now, regarding our AI complexity, there are several types. All 4 types are included. So the real complexity involves the uncertainty of our pool sensor inputs. The strip sensor, basically, it provides continuous output, but it can be unreliable in the event that evaporation occurs and the pool level becomes too low compared to where that static strip sensor exists, and it may actually limit and give us unreliable output. So the idea behind using that is simply, and it doesn't fully mitigate the problem, but it helps by putting the strip sensor at 3/4 high. It should be 3/4 covered by the water level, submerged, so that if there is some evaporation, it should still be centered on the sensor. Imaginary complexity involves the uncertainty of the hidden layers in the CNN and the fully connected layers, and we simply have to trust that based on this trained model and the trained scene, that the output is reliable. There can be cases in which the output of the CNN and the fully connected layers does not provide us with the proper output. And this is mitigated as was mentioned before, by combining this data with the motion sensor and the water activity sensors so that you don't have to completely rely on the output of this network and then in the layers to tell you if there's a person in the pool or not and their status. Rather, it just is a part of a whole in the algorithm that helps you determine the outcome or whether to alert the user. Periodic complexity is a serious problem with this system. Pool activity changes throughout the day. It can be highly likely in, say, 6 o'clock, 7 o'clock in the evening, but really unlikely to have activity at 4 a.m. So things like that have to be planned for and kind of assumed. Along with periodically throughout the day, illumination changes constantly from sunrise to sunset. And this is mitigated by, sorry, I wrote that twice, mitigated by storing memories, as I had mentioned before, and weighting them when relating the data. So when these events occur, when these different pool activity events occur, they can be stored and recalled so that we can kind of understand when these events might happen or when they might not happen, or rather when they're less likely to happen. Regarding illumination changes throughout the day, we can simply suggest that the pool user well lights their pool at night, as well as to deal with even the illumination changes throughout the day. We can train the model with background scenes at different portions of the day so that it should be able to have an improved ability to determine and subtract background different lightings during the day. Our combinatorial complexity involves uncertainty of changes to pool contents when a user decides to leave pool noodles, beach balls, things in the pool. That's going to trigger the pool monitoring system, and it will alert the user saying there's a non-human object in the pool. So the way this can be mitigated, as stated before, the weights change of the weighting algorithm over time. And so this is something that allows when you have an event such as this, the user is notified, they can acknowledge it, and over time the weight of this video or this image data recognition will decrease over time and de-escalate the weighting so that unless a new event occurs, such as a heavy activity in the pool or motion is detected, it will essentially assume that there's no activity. So if there are any questions, feel free to email anyone in the group with questions about the design, and thank you very much for taking the time to listen to our presentation.